Hi everyone. So yeah, as John said, I'm going to talk to you a little bit about a subject that or a lot of you will be very familiar with. It's heat storage, why and how we do it. So just briefly, I'm going to go over the heat capacity of different materials. So heat storage for future use has been used for hundreds of years, both in industry and domestically. And as I mentioned, it's certainly nothing new to commercial greenhouse owners. The typical heat storage system that we're all used to is usually to feed a hot water system. And more often than not, as a result, the heat transfer medium is also water. But if we just take a minute, why is this the case and why do we use water? Well, if we look at the physical properties of water in comparison with other options, such as thermal oil, ethylene glycol, etc., then it becomes clear that there are no other sensible options out there. No materials, when compared to water, have A, the heat storage ability, B, the practicality, and C, the low cost. If we take a quick example, we can see the problem a bit more clearly. The energy required to boil a kettle, assuming the kettle holds about 1.5 litres of water, and we want to raise the temperature from about 10 degrees to 100 degrees C, is 0.16 kilowatt hours. To raise the same volume of thermal oil by the same amount would require 0.075 kilowatt hours, or about half the energy. So you should be able to see that you would need about double the amount of thermal oil to store the same amount of heat as a kettle of water. Add to that the relative cost of water and the practicality of using water, and nothing else really comes close. So why is heat storage important? Well, with the increase in the use of alternate energy systems, things like biomass in the horticulture sector, as well as regular use of the byproducts of heat production, such as CO2 and electricity in some circumstances, it's increasingly important to ensure that heat storage is used to its maximum effectiveness. So what does heat storage enable you to do? Well, it offers some redundancy for one. For example, where multiple boilers are located on site. If, for whatever reason, a breakdown or perhaps servicing occurs, one of the boilers is out of action, then you can use the remaining boiler to fill the heat store during the day when heat isn't required, leaving you the capacity of the heat store and one boiler to make up the shortfall caused by the out-of-action other boiler during the night. In the same way, this can reduce your need for additional backup boilers. Heat storage also allows some flexibility with boiler or CHP sizing. Heat storage, in this case used in part as a buffer, removes some of the peaks and troughs in heat demand. Therefore, a smaller boiler can be used and less capital cost as a result. Linking into this, and particularly important for biomass boilers, a heat store allows you to operate the boiler flat out to fill a heat store rather than ramping up and down. This maximizes the operational efficiency of the system, particularly the boiler, resulting in less fuel burned for the same heat output. Finally, and importantly for a lot of edible crops, heat storage enables the use of a boiler or CHP to produce CO2 during the daytime when it's needed, and can utilize the heat produced overnight when heating of the greenhouse is needed. And just by means of an example, here we can see the mismatch between heating and CO2 demand. Put together a chart showing the heat demand during a 24-hour period and the CO2 dosing figures for a typical tomato nursery in a summer month. So how much heat storage do you need? Now that we've established some of the reasons why you might need to store heat, the question becomes how much you need. In old thinking, a general rule of thumb used to be 200 meters cubed per hectare for salad crops, while for operation of a biomass boiler, typically greater than 50 meters cubed per megawatt of installed capacity is required. That's not the whole story though. There are a huge number of other factors to consider in sizing your heat store, including technology used, just as I just mentioned, whether you're using biomass or CHP, peak CO2 requirements, glasshouse efficiency, and the crop growing conditions, just to name a few. So what would our ideal heat store look like, and how would it operate? Ideally, we'll be achieving a temperature of 90 degrees C from your boiler or CHP setup, potentially higher. So that's our upper limit. At the other end of the things, you'd want to be reducing your return temperature to the heat store to 45 degrees. That is, you're using practically all the heat available to you. A bit idealistic, but it gives us a good starting point. So using a 5-hectare nursery as an example, you can see the effect that temperature difference has on the size of the heat store you require. So if your heating system is returning water at a higher temperature than is necessary, and you've got a boiler that perhaps isn't performing, you can cost yourself masses of heat storage. The two examples here are, as I mentioned, a flow of 90 degrees and a return temperature of 45 degrees. You can see that would require a heat store of about 500 meters cubed. And arguably a poor operating heating system with a flow temperature perhaps 80 degrees and a return temperature of 55 degrees, you'd need a much bigger heat store. So a site that we worked with, which was struggling to achieve 80 degrees flow, and the greenhouse was returning 55 degrees centigrade water. Following a few small changes made to the heating system, which ran to the cost of about £10,000, much better flow and return temperatures were achieved. And this resulted in about 30% extra heat storage available using the same heat store tanks. So here I've come back to our 5-hectare example, except in this instance I've assumed that it is using a lot of heat, so 1 kilowatt hour per meter squared per day in the summer months. And this gives a daily heat requirement of about 50,000 kilowatt hours per day. I've also assumed a relatively inefficient operation of the heating system too. The flow temperature to the heat store is only 80 degrees. The return temperature, as stated here, is 55 degrees. And the total heat store required for this particular example would be 1,800 meters squared. Using a few new assumptions, for example, the lower heat demand of 0.5 kilowatt hours per meter squared per day for the greenhouse, and a slightly better operation of the heat system. You can see here there's a slightly higher flow temperature. Then we can see the heat store requirements decrease significantly, so 60%. I want to briefly look at some examples of how heat storage integrates with particular technology. So I'm going to start with biomass. The most efficient way to run a biomass boiler is to run at maximum capacity for an extended period of time, rather than on the heat demand of the greenhouse. By operating on the greenhouse demand, the boiler will be regularly firing up and cooling down. Therefore, there'll be a requirement to burn additional fuel to maintain the boiler temperature. Using a heat store allows the site to operate the boiler at full output for an extended period of time, as I just mentioned, which in turn means that it will be operating at maximum efficiency as far as biomass conversion is concerned. As an example, with a large enough heat store, a 5 megawatt boiler could operate for 8 hours flat out to maximize biomass conversion to heat. This would fill the heat store, which can then be used as and when required from the greenhouse. The size of the heat store required, again, would depend on the flow temperature of the boiler and the return temperature from the greenhouse. So in this particular example, given a temperature difference between the flow and the return of about 25 degrees, a heat store of just over 1,400 meters cubed would be required, while with better operation and a temperature difference of 40 degrees, the heat store would only be 860 meters cubed. A similar principle applies to gas boilers, which can either be run flat out or can be modulated to match CO2 demands where applicable. Using the same example of a 5 megawatt boiler, the boiler could run over a period of 12 hours at a combination of part and full load. The same size heat store would be required as for the biomass boiler. Again, it depends on the flow and the return temperatures to the heat store. And where CO2 is required, the equivalent production is 137 kilograms per hectare per hour. Bear in mind that this is based on a high heat demand greenhouse. So I think this example was 1 kilowatt hour per meter squared per day. A low heat demand site would obviously produce a lot less CO2. Moving on to the engine example, a gas engine example. For the same 5 megawatts of heat output, as was shown in the previous examples, approximately 8 hours of running time would be needed. Unfortunately, engines can't vary their output in the same way that gas boilers can. Therefore, the heat and subsequently CO2 output is consistent for all the hours of operation. The integration of a heat store solves the heat output problem, as heat can be stored and used by the greenhouse as and when it's needed. The heat store size will be the same, somewhere between 800 meters cubed and 1400 meters cubed. However, as the engine is generating electricity in addition to heat, the gas input effectively doubles over that of the boiler, which is only providing heat. As a result, the CO2 produced per day is roughly double. In this example, the CO2 is also produced over a shorter period, 8 hours, so the CO2 rate is significantly more than the boiler. As a result of these characteristics, by installing a similar thermally sized CHP engine on a site that is currently using a gas boiler, you could double the size of the nursery and retain the existing heat store size while meeting all CO2 requirements. Finally, the interaction of heat storage with a heat pump can be an interesting complementary technology on a heating system. As the efficiency of a heat pump goes down as temperature goes up, you want a heat pump to output a consistently achievable temperature. And for most heat pumps, this is around 55 degrees C. The sizing of this heat pump on the slide is a bit misleading, as it's unlikely that you'd be using a heat pump to provide all your heating demand. It's much more likely to have a heat pump operating in conjunction with a CHP or a gas boiler, as is shown on the diagram here. As a result of the low-grade heat production, it can either be used as preheat for a boiler or gas engine, as just mentioned, or alternatively, in addition, can be connected to its own heat store, which can then be used for grow pipe heating. Renewable heat incentive rates are still good on heat pumps. However, if your heat store is struggling to get down to below 40 to 45 degrees, then you'll need to look at your heating system first. So in summary, you should always look to increase the system efficiency before looking into additional heat storage. As we've discussed, some simple changes can affect the return and flow temperatures to and from a heat store, which will result in a greater heat storability. Integration of new technologies to a heating system can affect how heat storage is looked at. For example, in the case of biomass, the purpose is to ensure that the boiler can operate at its maximum efficiency. For gas CHP engines, CO2 and electricity production might dictate the size and operation of a heat store. And for heat pumps, the use of heat produced will determine whether a new heat store is required in conjunction to an existing heat store. And just in summary, there are a multitude of factors that can affect heat store sizing and its operation, all of which need looking into before designing or making changes to existing heat stores. I think that's it.